Welcome back to our C++, parallel C++ for scientific computing class. Well, last time we talked about a fixed point algorithm, which I developed during the lecture. And afterwards, I was criticized by Panos, saying, hey, why did you introduce that? It's just a glorified for loop. Because all what you do, you supply all the information in addition, well, the termination clause, the body, and the initialization to a function, and all what's left inside that algorithm is actually a for loop. Why do you do that? Well, my first knee-jerk reaction was std for each is a for loop as well. Std copy is a for loop. Std transform is a for loop. Std unique is a for loop. All these algorithms, or many of the algorithms, are actually just glorified for loops. But that is not the main reason why I introduced that. Code is generally written not for the computer, but for people. Because either you write it and somebody else will have to maintain it for the years to come, or you yourself have to remember 8 weeks later what you actually have been doing. And if you look at the code that actually uses an algorithm which is called fixed point, you don't even have to think about it anymore. What the hell is the code doing? Because the function name gives it away. Whereas when you have a for loop, you first have to figure out what is that for loop doing, what is it initializing, what's the termination condition, and the code is very confusing possibly and requires a lot of time to remind yourself what you've been doing 8 weeks ago. There could be also the case that the fixed point algorithm itself is used many times in the code base, and each time the for loop is written slightly differently. In one place you use a while construct, in another place you use a for loop, and so on and so on. So just from looking at the code, it's it's more difficult to discern what is that for loop doing. Instead, if you replace it with a function where you can specify the name and it's clear what this thing is actually doing. Based on this insight, the whole standard template library has been built. The whole library that comes with C++ has been developed in the last decade of last century and very much in the early years of this century. And we will talk about that today. Just imagine the following scenario. You have to write a code. The company asks you to do that. But the company said, for this code to work, you have to consume the data written by Joe over there, and you have to consume some other data which was written by Jill from another company. And both are different types of programmers. Joe's data is provided to you as an allocated array of integers, and Jill's data is provided to you as a list of doubles. And you have to analyze both data in the same way. For instance, you have to find the minimal value or the sum of all values and so on. So what you would like to do is to be able to write the code once. You don't want to write two different things just to be able to consume different data provided by different people. And this is a very common scenario in software development. You are seldom sitting in an ivory tower and you're closed up to the external world and you're kind of closed onto yourself. Most often you have to deal with data or with interfaces or with other libraries that come from somewhere else or have been developed 10 years before you were born in the same company you were working. That is the gist of what C++ calls generic programming, and we will kind of dig into that today, and I will try to explain that a bit more in detail. Now, you might ask, why do we talk about these things? Why? This is a class about parallel C++. Why do we talk about for loops? I hope to give you an answer to that in the end of this lecture as well. And I hope to convince you that using the standard template library and the paradigms that are introduced by the standard template library in your own code, which will help you to write much better code in the future. And I will try to make that argument over this course of today's lecture. So we will talk about the C++ standard library. Well, not about the whole thing, but mostly about containers and algorithms today. Next lecture, I will continue the discussion of that, where we will talk more about iterators and ranges and related concepts. Okay, so the standard template library, which is part of the standard library, the abbreviation mostly used is STL. So if you see STL, people usually refer to the standard template library, which is a subset of the C++ standard library. Is a very extensible framework that deals with data and algorithms in your C++ program. So I will present the general idea, then some fundamental concepts and examples of containers and algorithms. And I will talk about generic functions in the middle of it, just to drive home the message I started to develop last time, and to give you more examples on more incentives to actually do work with these tools that are available to you. Today we can already write programs that are very similar independent of the data type, right? You can write a loop that works with integers. You can write a loop that works with arrays of doubles, and these loops look very, very similar. So you can use a standard vector of ints, and that is not very different from using a standard vector of strings or a standard vector of doubles. We have to deal in programming with very, very common tasks, with a full set of tasks that are repeated essentially perpetually. So we want to collect data into containers. We want to organize that data for printing, for fast access. We want to retrieve data items by value, by index, by certain properties the data exposes. We want to be able to add data to collections of items. We want to remove things. We want to sort. We want to search. We want to do numeric operations on all of those, and so on and so on. So, as I already mentioned, in a perfect world, we'd like to write common programming tasks so that we don't have to redo the work each time we find a new way to represent our data in memory. And we want to isolate the gist of a certain task completely from the representation of the data we are dealing with. Just as an example, finding a value in a standard vector isn't at all different from finding a value in a stat list. Looking for a standard string, ignoring the case, is not that different from looking for a standard string where you don't ignore the case. Graphing experimental data with very concrete, with very exact values is not that different from graphing data with rounded values. Or, as a last example, copying a file is not that different from copying some array in memory. So all these things have very common properties and represent a certain set of functionality we want to isolate from the concrete use case where we apply that algorithm. And that is what the standard template library achieves. Let's continue with some criteria what we would like for our code to be. A whole programming language was developed a long time ago under the premise of write once, run everywhere. Well, it's Java, we know that. And so there was a demand for being able to not rewrite software constantly over and over again for the same task. And this is what we would like to achieve in C++ as well. So we want to have code that is easy to read, because we forget easily. We don't know 8 weeks from today what we actually were thinking when we were writing code. We want to have code that is easy to modify, because customers constantly come up with new requirements. So we have to go back to the code base that has been developed over a long time and add features, change things, fix problems. We want to have code that is regular, so that if you understand how to deal with a vector of integers, you don't have to learn new things just to understand how to deal with a list of strings. It's the same thing in the end. We want for these things to be fast. in one of the lectures, I showed you how quickly and how easily it is possible to fall into the trap of parallelization. You parallelize code, and suddenly it's 100 times slower than the sequential code you had before. So why reinventing all these things and running into these issues over and over and over again? We want to be able to reuse existing modules so that we don't have to invest time into solving these problems over and over. Just another set of criteria to make the perfect world even more perfect. We want to be type safe. Even if we work with arbitrary types, we still want it for it to be type safe. So we want to be sure that the compiler can tell us when we make mistakes. We want for the data storage to be compact. We want to be able to access data fast and so on. And as I already said, there is a set of commonly applied tasks you need every day. So why start reasoning about these tasks every day from the beginning? Just some examples, and these are really just the tip of the iceberg and mostly completely superficial, but just to give you a variety of problems we have to deal with every day. Sorting a vector of strings, finding a number in a phone book, find the highest temperature, find all values that are larger than a given value, find the first occurrence of a particular value, sort the telemetry records by unit number, sort them by timestamp, find the first value larger than Peterson, what is the largest amount of seen so far, and so on and so on. So you can think of 100 other tasks that go down the same way or have the same gist, but in the end encapsulate and require a set of very basic operations in order to be implemented. That person, Alex Stepanov, is by training a mathematician. He was in the Soviet Union, left in the 70s, lives in the US today, and is one of the godfathers of generic programming. It's actually the person that has developed a lot of ideas around that, based on the idea that programming is math. He's a mathematician, so what he did, he developed methods that allow you to reason about code based on mathematical abstractions, which is just incredible. And he is the main designer of the standard template library, which was adapted to the C++ standard in 1998. So in my book, the C++ standard library, the STL, is one of the marvels of human engineering. You will not find that, or you will be very hard-pressed to find something similar in other domains in terms of cleanliness, structure, uniformness, and so on. And we will see what I mean in a minute. So let's do an example. How do we get from concrete code to a more generic representation? I've done that last lecture on the fixed point, at least to some extent, but let's do it again. Let's say we have an array of doubles where we know the size, and we want to find the sum of all of those elements. It's a very simple algorithm. We just loop over all the elements in that array, add them up, and return the sum of them. Easy. What about if we have a list? Somebody created a list where there's a node type which has a pointer to the next node, and it contains some integer data, and we want to find the sum of all those integers. Again, the function takes the pointer to the first of those nodes, and then it iterates over the list by adding up the data and then going to the next node until you go to the end of the list, which is when the pointer turns to be 0, right? That's the end marker of the list. So two completely different sets of data, two completely different set of algorithms implemented, in the end do the same thing. Both find the sum of all elements of some type of container. So if you try to generalize a bit, if you lift that and make that a bit more abstract, I wrote some pseudocode here. if you look at that function, what that sum function actually does, it receives some data, it has a loop which goes until it's not at the end of the data, then it gets the value of the current element, sums it up, and goes to the next data element in our data structure. So in other words, we need just 3 operations on the data structure that allow us to implement these algorithms. And as long as we have these 3 operations, we can write an algorithm that is applicable to any of those data structures. Namely, we need not at the end, we need a get value operation, and we need an operation that gives us the next element in the sequence. This is how this code looks in C++ today, and I will explain things a bit more as we go. For now, let's assume we have 2 things which C++ calls iterators, and we will talk about iterators a lot, where the first argument points to the first element I want to start with, somehow refers to it. The second argument refers to the end of my sequence, somehow. And an argument t, which in this case is the accumulator value. Essentially, we let the user initialize the accumulator from the outside, pass in the initial value, and then we use a while loop to go over our sequence to find the sum. How do we go over the sequence? Well, we do as long first is not last, as long as our reference to the element has not reached the last element yet, we add up things by dereferencing that thing that points to the elements. And C++, if you know pointers and C, it's essentially the same syntax. C++ has just decided to use the dereference operation to refer to the value, which is our get value. And then it moves our iterator to the next element by just incrementing it. So that increment operation just moves it forward, and then we can continue that as long as we need until we reach the end of our sequence. What operations do these types, iter and t, must have in order for this function to work? Well, the iter type should be what's called an input iterator. It's just a concept defined in C++, and the concept is a set of type properties. We talked about type properties in the beginning, right? So an iterator, an input iterator, is a type that supports 3 operations. You can compare it, you can increment it, and you can dereference it. And any type that exposes these 3 operations is an iterator. That's all what it needs to be one. So if you ever want to become an iterator, you have to support these operations. You have to be able to compare yourself to something else. You have to be able to increment yourself, and you have to be able to give back the value you're referring to. T, on the other hand, should be something that supports the plus operation, and just the plus operation. That's all what it needs. Well, it needs the assignment. But since we assume that all our types are at least semi-regular, this is kind of a given. We talked about that in the beginning. So t has to be regular in addition to supporting the add operation. And if these conditions are true, then this algorithm will work. Regardless of where the iterator is pointing to, regardless what the type is the iterator is referring to, as long as these type properties are fulfilled, we can use and apply that algorithm to do what we expect it to do. So as an example, we create an array of floats, 1 to 8, and then we can use our algorithm by passing the begin in. The array name is the pointer to the first element. A plus size of A will give us the reference to the last element. Well, not quite the last element. It will point to the element after the last one, and I will talk about that, why that is important. And then we pass in the initial value for our accumulator variable, which in this case is 0 as a floating point number, and the algorithm will just compile and will work. So let's talk about how this actually works. As you see, this is almost the standard algorithm reduce we have seen many times over. several times. It's a bit simplified just for the terseness, but in the end it's the same what standard reduce is actually doing. And it happens to work for C arrays, for vectors, for lists, for istreams, for maps, for sets, for unordered, for hash tables, for any data structure that exposes iterators that conform to those type properties. The code in the end will run as fast as you can write it in assembly. The compiler will make sure that it will generate optimal code. And the code requirements on the data have become explicit, which is also very important for your understanding. Because if you understand what are the requirements on the types you're using, you understand what the code can do and can't do. So you can start reasoning about the code, which is another very important thing you want to learn when you write code for a living in the end. Okay, so let's talk about the STL in a bit more detail. Again, Alex Stepanov is a designer with a general aim that he wanted to create the most general, most efficient, most flexible representation of those type concepts, containers and algorithms, and combines those concepts freely wherever meaningful. In other words, what he tried to do, he designed a set of functionalities that fulfill the requirements are listed. Those things from the perfect world I listed in the beginning are implemented in the standard template library. So it gives you exactly what you want as a programmer. His aim was to make programming like math, or good programming is math, is his motto. It should work for integers, for floating point numbers, for any type you might want to come up with. And if you're curious, read this book, Elements of Programming. It's a very hard book to read, but it's worth doing. And I believe that every programmer who really works in C++ should have read this book at least once in his life. By the way, it took me about 3 years to read the book for the first time. So it is a very difficult book to read, but it's an eye-opening book because it establishes the connection between abstract algebra in math and C++ generic programming, and allows you to apply the math concepts that have been developed over 2,000 years by humanity directly to working with C++ code, which is an immense helpful thing to do. Okay, so the basic model of the standard template library is the following. You have two major categories: containers, which store the data, vectors, lists, maps, hash maps, you name it. About widely known, widely used, about 20 different container types for different performance properties. And on the other hand, algorithms. Things like sort, find, search, copy, for each, transform, unique, reduce, and so on and so on. About 100, 150 algorithms are there. And the trick is that these two things are completely orthogonal. The containers don't know anything about the algorithms, and the algorithms don't know anything about the containers. The connecting piece between the two is what is called iterators, and that's those things that are exposed by the container. They know about things, how the container internals work, and allow the algorithms to work with the container in terms of the iterator operations. These three operations I mentioned. So it separates the concerns of containers and algorithms very nicely. As I said, the algorithms manipulate the data without knowing what the container is. The containers store the data but don't know anything what the algorithms do. And the algorithm containers interact using iterators only. So all algorithms are written in terms of iterators, where each container has its own iterator types, obviously. The iterators know how the container internal structure works. And iterators expose a uniform interface that allows us to write these algorithms in a uniform way. We will see some examples. So today we have a dozen or so containers in the standard library, over 100 algorithms connected, and these two are connected by iterators. There are other organizations provide more containers and more algorithms. And the beauty of that is that you can write your own container, and as long as it conforms to the rules, you can directly apply this container or any standard algorithm to your container. Likewise, you can use a standard container and write a new algorithm that directly can use any of the standard containers without having to be modified for different container types. So it's a fully extensible way of writing code and for applying things and for making programming happen. So as I said, it's probably the best known and most widely used example of generic programming, and it's a marvel of engineering, just from the conceptualization phase up to the implementation. The benefit of using the STL is, once you know the basics, you can kind of extrapolate the rest. You don't have to know everything. You know how to use a for each with a standard vector. That gives you immediately the knowledge how to use a list of strings and sort it. Same thing. So let's look at the basic model. How does that work? Each container that has somehow stored a set of elements exposes two iterators. The iterator referring to the first of its element, and an iterator referring to the element after the last one. And that is important. We will talk about that. So the end iterator never refers to the last element in a container. It always refers to the element that comes after the last one. An iterator is a type that supports iterator operations, nothing else. So don't start thinking about what is an iterator. Well, an iterator is just a type that supports these three operations. Plus plus, go to the next element in the container. Star, get the value of the element I'm pointing to, I'm referring to, and equality, does this iterator refer to the same element as that iterator? So equality doesn't compare the iterators, it compares the element, whether it points to the same element or not. There are more powerful iterator types that support more operations, like going backwards, minus minus, or indexing and other things. But that is not important to understand the basics. Okay. So let's look at containers. Containers are special data structures that help storing one or more elements of another type. So it's collections of items. Containers manage the storage space for those items they store and provide functions to access them, like a standard vector, right? Like an array. An array is just one possible type of containers. Containers replicate structures very commonly used in programming. We have arrays. In C++, arrays that are dynamically resizable are called standard vector. Static arrays in C++ are called std array. We have linked lists like std list, which is a bidirectional list. We have a forward list, which is a unidirectional list where you can iterate only in one direction. We have trees, which are called set and multiset. We have hash sets, which are called unordered set. We have associative arrays like maps, multi-maps, unordered maps. We have various adapters on top of those, queues, priority queues, stacks, and associative interfaces for arrays that allow us to represent a vector as if it was an associative map-like data structure. They are called flat map and flat set, just in case you want to know. So a multitude of very well-known, commonly used data structures that are all built in a uniform way, and you can use all of them with the standard algorithms that are defined in the library. But the containers hold the sequences in different ways, obviously. If a standard vector is just a consecutive sequence of elements in memory, like an array, which is referenced by some root object, which is the standard vector itself. It exposes the begin and end iterator, obviously. The begin iterator refers to the first element in the vector. The end iterator from a vector refers to the first element after the last one. If you look at the same for a list, which is a bidirectional list, well, you have nodes that are arbitrarily distributed across memory, but they are linked with pointers. So one node points to the next one points back to the previous node. Again, we have some root, which is the standard list itself, and we have a linked list of elements where the begin iterator refers to the first element and the end iterator refers to the element that would come after the last one. Or a tree data structure, like I said, which is a binary tree. And again, it exposes a begin iterator, which refers to the first element. And when I take that one and increment it, it will traverse the tree data structure in sequence based on the ordering criteria of my set. And the end iterator refers to that element which comes after the last one. So that already tells you that the way these things are being built is very uniform. And since all of them expose begin and end, and the algorithms work in terms of iterators, you can already start seeing where that goes. Namely, you can apply all the algorithms to all these data structures uniformly. Just some examples. Let's talk about dynamic arrays, which is essentially a standard vector. All the containers are generic types. And we talked about type functions at some point, where I said a type function or a template type is a type function that converts one type into another. And what standard vector does, it converts any type T into a data structure that can hold one or more of those T's. So it's a type generator. It generates a container that can store T's. I said that many times, I will say that many times over. The general rule when it comes to selecting which data type to use in modern computing, and that is not only true for C++, but especially for C++, use standard vector as the data type of choice. And if you believe that you can't use standard vector as a data type, think again and use it anyway. Find a way to use it, because that gives you at least 10 times better performance than any other data type you can use. And we talked about that, for why that is the case. Mainly because they rely on contiguous memory, which makes access of the items a O1, a constant time operation. It doesn't matter which element I'm referring to, it always takes the same amount of time. But you have to be careful, certainly, with these kind of data types, because insertion and deletion could have linear complexity. Why is that the case? Why is it has insertion of elements in a standard vector ON complexity and not O1 complexity? So in other words, it depends on the size of the vector how long the operation might take. Why is that the case? Anybody? We will see it later on, but what happens if I have a sequence of elements and I want to insert a new element here? What do I have to do? I have to extend the memory. I have to copy that guy here. I have to copy that guy here. And then I have room to insert my element. That means I have to do at max n operations in order to insert something. If I want to insert something in the beginning, I have to move all elements. And if I have 1,000,000 elements, that might take a while. But if you insert at the end, obviously, you have O1 complexity. But be aware that arrays and vectors have that property that deletion and insertion may be very expensive. Let's do an example with standard vector. And we have seen some of those, but I want to kind of drive the message home how you can use them and how easy to use it is. We define a new vector, fill it with 5 integers. Then we can refer to any of the elements of the vector using the indexing operation, like a normal array. It's like you would expect from an array. You can have vectors of vectors, right? A vector is regular when the element it stores is regular. So that means that we can build vectors of vectors where each element in one vector is a vector itself. So you can think of it as a two-dimensional data structure, which allows us to double index them. if you want to. So that's one way of representing two-dimensional data structures. And also, the indexing operation gives you something you can write to. So you can modify the element. It's not only that you can read the element, like here, you can write to the element and then access the changed element later on. Okay. You have to be careful, though, that you don't access an element that doesn't exist. So your index should be in the range between 0 and the size of the amount of elements you have stored currently in the vector. There are many debugging tools available that help you with that. So if you want to be sure that you don't use the indexing operator out of bounds, use the .add function, which is defined on the vector, which will do the boundary checking for you and will complain if you're trying to use an index which is invalid. By the way, using indices which are out of bound are one of the major reasons for vulnerabilities in software today. Not only in C++, but in C as well. So whenever you have to do an update of your operating system, be aware that probably somebody messed it up 15 years ago and somebody was using an index that goes out of bound of arrays. Because that out of bound indexing amounts for, I don't know, 60, 70% of all vulnerabilities people have discovered in code. Okay, let's sidestep from here a bit and let's talk about generic functions. Most of the functions we have seen so far have used concrete types, which seems natural because when you write a function, you know you want to work it with doubles, so I declare the argument types as doubles. But we have seen functions where that's not the case. Reduce, unique, we have seen the sort function, and so on and so on. And those functions are essentially usable with any appropriate type for any container. And that implies that we do not know the types at the point when we actually write our algorithm. So when for each is being written or fixed point was written, in the end, I didn't know what types the people might use when they use the fixed point function. And only over the lecture we discovered that we can apply it actually to a wide variety of situations, a wide variety of data types. And this is called a generic function. So it's a generic function in C++ is a function that can be used with arbitrary types. And we do not know what types, or the designer of the function can't know what types other users will use when that function is being invoked. So we have to find a way to define the concept of what exactly does it mean to have arguments that are appropriate for a function. What can we know whether a function will actually work for a given set of argument types? And I already hinted at that with that sum example, because the answer is kind of twofold. The first side of that answer is that as long as a type supports all the operations that the function invokes, it will work, right? In our sum example, t had to be addable. You had to be able to add 2 of those t's in order for the function to compile. If not, you would get a compilation error because the compiler will say, hey, you're using that function with type ABCD, and that ABCD, I don't know how to add that to another ABCD. So the function will not compile. So the function, if the function does x plus y, that implies that the types of x and y have to expose a plus operator that supports that operation. Otherwise, it will not work. And the implementation, when the compiler instantiates the template function, it checks whether x plus y is actually defined, and if yes, whether types x and y support that operation. The other part of the answer is that the standard library actively constrains the type requirements for certain things. For instance, iterators, right? All the algorithms take iterators, and the standard library enforces that the types you use to call unique or to call sort actually expose those properties. whether they are iterators, whether they support dereferencing, incrementation, and comparison. Modern C++ libraries do that using C++ concepts. As I said, a concept in C++ is a set of type requirements that are being checked. And we will see an example in a minute. So let's go back to our sum example. And this time I added, instead of simply saying iter has to be an arbitrary type, now I tell the implementation that iterator actually has to be something that conforms to the concept of being a standard input iterator. And standard input iterator is a concept that is predefined, which will require for iter to have these three operations. So it will check whether that type actually exposes these three operations. I defined my own concept, saying edible. T has to be edible. And if you are interested to see how that's implemented, it's fairly straightforward. What you can do in C++ nowadays, you can say, OK, I define a new concept, edible, of a type T. And if for this concept to be true, to be applicable, what has to happen is that the body that comes afterward compiles. Nothing else. So as long as the code inside that body compiles, the concept is true for T. If the body doesn't compile for whatever reason, the concept is false. So that means that, what does that mean? It means that it requires that edible applies to two instances, A and B. The operation of A plus B has to be valid, has to compile, and it has to yield a result which is the same as the original T. As long as this is true, edible will be true, and then this function can be compiled. Otherwise, the compiler will say, hey, your type T is not edible. In other words, when type T doesn't have a plus operation that allows two instances of T to be added to each other, this function will not compile, and you will get a very nice error message. Compiler will tell you, you're trying to do something the algorithm doesn't support. And here we come back to the type properties I tried to explain in the very beginning when I said type properties is one of the most important things you have to keep in mind when you do programming. What do your types support? And when it comes to generic functions, this is even more important because generic functions can actually be used with any type, but then you might get very complicated error messages. And if you ever have done more complicated C++ programming, you will know that generating 30 megabytes of error message is not that can happen every day. And in the end, all you did, you forgot a semicolon somewhere. And concepts help you to alleviate that issue, that you don't get these horrendous error messages anymore, because now the compiler can check at the definition whether T is actually edible and can tell you that what mistake you made. So let's have a look at another example. I want to calculate the median of a sequence of elements. So let's reason about that, how we can do that. And we want to be able to compute medians for arbitrary types and not just for vector of doubles or something like that. So we go with a generic function that is implemented as a template function, as I showed before. You use the keyword template and define the parameters as being something that is supplied at compile time. So a template function is a single definition of a family of functions. So a template function is not a function itself. It just tells the compiler how it can generate a function from it when the concrete types are being supplied, when the user actually invokes that function. It uses types as parameters, so it relies on the knowledge that different types will have common properties and behaviors in order for the function to compile. So template functions are written in terms of that common behavior, being an iterator, being edible. When a function is actually being used, when you write code that uses the sum function, the compiler can deduce the types automatically. It looks at your argument types, sees, oh, okay, he's using a vector of doubles, so I instantiate my sum function for a vector of doubles. When the function is being called for a list of strings, then the template function will be generated for a list of strings. So there's no need for you to explicitly specify the type of the arguments. The compiler will be able to figure that out for you. Let's do it for median. Well, it's a simple implementation of calculating the median. The median is defined as the midpoint of a sequence of doubles, for instance. When you sort the doubles, then you take the middle element of that sequence of doubles. The only trick here, well, you have to sort it first to get the sorted sequence. And the only trick is that if the size is odd, you take the middle element, and if the size of your sequence is even, then you take the average of the two middle elements. And this is what this code is doing. So it's not very complicated. You can look at it later. I will not explain it too much. Standard median implementation. But what if we want to use that not only for vector of doubles, but we want to use it for vector of anything? Vector of int, vector of list, floats, of these homongous float 100 types I was mentioning last time, and so on. Well, all we have to do, we have to say, okay, t is now a template parameter, and that allows me to use, otherwise the function hasn't changed at all. The function itself, the body, is absolutely the same. The only thing I did, I turned that double into a t and let median return that very same type, which allows me to write the code like follows. I can do a standard vector of int, call my median function. It will work. Standard vector of doubles, call my median function. It will work. And as you see, the compiler deduces a type from here and extracts the type properties based on that. What you need to know is that the deduced template parameter type pervades the generated function. So it is not only the declaration that changes. Once t has been determined, it's clear that the elements of the vector are actually t's as well. So the whole function will be compiled in terms of that particular t, or double, or integer, or float, or whatever, which I supply. Okay? So template functions are a very, very useful thing because they allow you to write something once and then use it for arbitrary things, as long as the type properties of those arbitrary things are conforming to the requirements of the function you wrote. So when the template function is called, the compiler instantiates that template for the concrete arguments you supplied. And the only thing that can't be deduced is a return type, unfortunately, but all the argument types are being deduced. The downside of this is that it requires for the compiler to see the whole definition of the function. You can't have that function defined in a separate compilation unit. You have to define that template in a header file so that the compiler sees it. And that means if you do that pervasively, you have compile times that are much higher than what you're used to from other programming languages, because a lot of code has to be processed by the compiler this way. So again, what's an appropriate type when instantiating a template? For median types stored in the parsed vector, they need to support addition and division, right? I need to be able to find the midpoint, the average of two values. But we can have, even if we apply all of that knowledge, there could be subtle problems. And I want to kind of make you aware of those subtle problems by giving you some examples. Let's say we have a vector of doubles, and we use the standard find algorithm, which will look for zeros in the sequence between VD begin and VD end. This code is perfectly fine. It will work. If you do the same with reduce and supply 0 as the value for the initial value for the accumulator variable, you will run into problems. Anybody knows what the problems are? What could be? I'll show you the code in a minute so you can see it for yourself, but just from the top of your head. Anybody sees what problem could be caused by that reduce invocation? No? Well, let's look at the code and then you will see for yourself. This is implementation of find. It takes two iterators and the value I'm looking for. So it is a loop from the first to last, incrementing first. And if the current value you get by dereferencing first is equal to the value, it stops looking for it and returns the reference to the current element, so that you know I found the element. If no element is being found, it returns the end iterator, the second iterator I pass into the function, which allows me to check afterwards, hey, did you find something or not? Just by comparing whatever the function returns with whatever I passed in as a second argument to my function. Everything's okay. And if you look at the code before, what will be t in this case? So this will be deduced as two vector iterators, but what will be the type of the third argument when the compiler compiles that? What will be t? What will it be? What is the type of 0? What is the type of that 0? It's an integer. So t will be deduced as an integer, which is fine, because even if I compare it against a double, that comparison will do the right thing, because comparing a double to an integer is okay. But if I do the same thing for std reduce and t will be deduced as an integer, then the whole accumulation will happen in terms of integers, even if the sequence is doubles, which will lead to truncation errors, right? Everybody sees that? Who doesn't see it? Make sense? If t is deduced as integer, then this arithmetic operation is an integer equals to an integer plus a double. What happens when I add an integer to a double? This is converted to a double, everything's fine, but then I assign it to an integer, which leads to silent truncation of your result. So your reduction operation will be done in terms of integers. It might be what you want, but you have to be aware that in this case, if you really want to do that, you have to pass a 0.0 here as a second argument to force the compiler to deduce the accumulator type in a proper way. Make sense? So with that deduction, as convenient as it might be, there could be various problems associated with it. Another problem students usually run into, or many people run into, is that there's an algorithm which is std_max. Std_max returns the reference to the larger of the two arguments. So it will tell you which of the two arguments is actually the bigger one. Okay? But the implementation of std_max requires that both types are the same. That the first argument has the same type as the second argument, because the implementation looks like this. It's max, t left, t right. And since I use t for both arguments, the compiler can instantiate that only if both types are the same. Otherwise, if it deduces different types, that function doesn't apply. So you will get a compilation error if you use max with different types for the arguments, which is kind of weird. But it's a problem that was caused by the language capabilities we had when the function was added to the standard in 1998. Because what would we have to do to alleviate that? We would have to use T1 and T2 as two separate types in the template parameters to allow for the compiler to deduce these two things separately. It might still compile, everything might be okay, but what type should we return in that case? What is the return type of that function? You can't really figure that out, right? Is it T1 or is it T2? Is it an integer or is it a float? Is it a double or what is it? And since the language didn't allow us to resolve that in 1998, the function was added with the same argument requirement as it is. Now, nowadays you could write it this way. You could say, okay, compute the return type and compute it based on whatever this expression gives me. So if the expression gives me a double, it will return a double. If the expression gives me an integer, it will be an integer. But since standards are done for longevity, standards can't be changed. The max function was never updated in the standard. So you have to be aware that when you use standard min or std_max, that you have to supply two arguments that have the same type, otherwise it will not compile. So as useful argument deduction for template function is, it can lead to unexpected results if you're not aware of what the caveats could be. That's why I'm listing those. Does it make sense? Yeah? Okay. Let's look at some algorithms. We already had a glimpse into some of those, but I want to drive home my point a bit more. So let's say we have the find algorithm defined like this. It takes two input iterators and a value, and I wrote out the requirements for that algorithm, at least partially. I didn't bother to do that. You see what the requirements are, right? It's really just requirements on the input iterator, and value has to be a regular type, essentially. That's the requirements. Otherwise, you can't compare it against other things. So how does it look like? I have a begin iterator. I have an end iterator, which refers to something beyond the end of the sequence. But what do we need? We need the comparison. We need the dereference. And we need the increment operation, which tells us that in has to be an input iterator. Okay? So if that is the case, then we can use our standard find with a vector of integers, obviously, because a vector of integers exposes iterators. So v begin and v end, which are the begin and the end iterators for this particular vector, are input iterators at least, so everything will compile just fine. What about if you want to use it with a list of strings? Not with a vector of ints, but with a list of strings. It will work, because list is a data type that exposes a begin and an end function, which gives us iterators, which are input iterators, and acts as a string, which is a regular type, so we can invoke find with those list of strings just fine. The same is true with a set of doubles. A set is a binary tree. It stores doubles. It exposes the iterators. So we can use did find in order to find something in a nested set. You see where that goes. So we have a function definition once, but we can use it in arbitrary contexts with arbitrary types as long as those types have the properties required for find, which in this case is really just a minimal constraint. You have to use iterators and you have to use a regular type to compare with. That's it. Okay. Let's talk a bit about what an iterator actually is and why do we use the notion of an end iterator pointing to the element after the last one. So an iterator refers to an element in a sequence. It's just a means of telling I'm referring to this element. The end of the sequence is always one past the last element. This is necessary to elegantly represent empty sequences. Because if the end iterator was pointing to the last element in the sequence, not the one after the last element, if the end iterator was pointing here, what would it point to when our sequence is empty? We have no way to represent that. And that's why the end iterator always points to the one after the last one, which allows us to nicely represent an empty sequence, in which case begin and end are just equal. Okay? Because if begin and end are equal, all the algorithms will not do anything, because all the loops go from the first to the last. And if they are equal already, nothing would happen, right? So that is one thing you have to really remember, that end iterators are always referring to the element after the last one. You can compare with end iterators, but that's all you can do. You can't dereference them, because what happens when you dereference the end iterator? You get an out of sequence, right? You're trying to access an element that doesn't exist. So never dereference a end iterator. But you can compare with them just fine. So another example is find if. Find if is a algorithm which goes over the sequence, and instead of having a value, it receives a predicate. A predicate is a function that returns true when some predicate is true. And what it does, it gets passed in the current element, so you can compare with you can make more complicated search algorithms. Not only compare with a value, but you can compare based on other conditions, and we will see some examples. For instance, if you want to find odd values in our sequence, the first odd value, well, what we do, we pass in a function which we call odd, and odd is supposed to return true when its argument is odd. And then our findIf will give us a reference to the first odd element it found, right? It goes over the sequence, and for each of the elements, it checks whether the predicate is true, and if the predicate is true, it drops out of the loop and returns the reference to the one it refers to. So let's talk about predicates a moment, just because I always try to introduce C++ features as we go. In the simplest case, it's a simple function, right? It's a function called odd, takes an integer, returns a bool, and it returns true when the integer was odd. Right? If the remainder of the division by 2 is not 0, then the thing is odd. That's what this function does. So I can invoke odd with a number, and it will tell me, yeah, it's true, it's odd or not. C++ has a very interesting feature, and we haven't mentioned that, and that is a very useful thing, is that you can turn every type into something that can be invoked as if it was a function by defining a special operator, parenthesis, which will be invoked whenever I use an instance of that type as if it was a function. So I define a struct odd with that function operator. I define an instance of odd, and now I can invoke it as if it was a function. And whenever that happens, this operator is being called. So that's very useful, and we will see some use cases for that. And last but not least, obviously, we can just use a lambda, right? Why not use a lambda? We talked about lambdas last time, and our lambda returns the remainder of division by 2 for the argument. We assign it to a variable called odd, and then we can invoke it as normal. So any of these three things we can pass to our findIf algorithm. And that is what I've been doing with the fixed point last time, right? We were passing functions code to the implementation of the algorithm, and we are customizing the functionality of the algorithm by providing our own functions, our own body, our own termination condition, our own initialization. The same is true for all the algorithms in the standard library. So another example where function objects could be very useful because they can have members, they can have state. And that means that I can create a less than with a value and then compare in the operator against that value, which allows me to write this. FindIf in my sequence anything that is less than 43. Right? That 43 is stored in my object, and whenever findIf invokes that operator, it compares against that 43 and gives me true if the current value in the sequence is less than 43. But you can do the same with a list of strings, just finding the string perfection, and so on and so on. But again, we could just use lambdas here, right? And I believe on the next slide I have the same thing written as lambdas. So in some sense, you can think of function objects as things that are equivalent to lambdas, or lambdas are equivalent to function objects, which is how they are implemented anyway. Okay. So again, the standard algorithms are written in a way that they encapsulate the core functionality of some operation and provide you the means to customize that operation through arguments that you can pass to the algorithms, like findIf. You pass a function which customizes how the findIf operates and how does it do its work. You can use that even for more complicated things, like let's say we have a record, an employee record with a name and an address. And what we want to do, we want to find somebody by name. Right? We have a vector of those records where I have two entries, and I want to find Donald Duck in there. And I want to find the entry that represents Donald Duck. How do I do that? Or I want to sort them based on their name, or I want to sort them based on their address. The first invocation, which has some comparison predicate, will compare by name, so the sequence will be sorted based on the name. And the second one, the sequence will be based on the will be sorted based on the address. So let's have a look how these things can be implemented. Compare by name is nothing but a function object that receives two records from sort. And instead of comparing A to B, I compare just the name of A against the name of B. And that will make sort things by name. The second one's compare by address. I do something similar, but this time I compare the addresses of my records. And then the sort will sort things based on the address. Just by supplying some additional customization to the sort algorithm, I can control how what is actually being sorted and what criteria is being applied to the sort. By the way, I can use that to reverse the sort order, for instance. Instead, normally sorts using the less than operation. But if I want to have a descending sorting, I just supply the greater than operation there. And then sort will actually do a sorting in descendant order and not in ascending order. Okay. Let's have a look at how does a vector look in the implementation. So it obviously has some pointer internally which points to the array of the current elements. And then it exposes its iterator types, which are usually unspecified. Nobody knows what those types are except for the vector itself, so I'm not showing them. It exposes a begin and an end function, which gives me the reference to the first element and to the one after the last one. And just as an example, it has two additional functions, arrays and insert, and we will look at those, what happens when you apply those. So let's say I have a vector which has a bunch of elements. I ask it for its begin iterator, increment the begin iterator 3 times. Then I assign whatever I got to another iterator and increment the other iterator again. What we will get is this. I start off with a vector of 6 elements. vBegin gives me that reference. I increment it 3 times, 1, 2, 3. And then I initialize Q from that position and increment it again, and Q will point to the next element. Now, what happens when I insert a new element at the position P into the vector? This will happen. It will shift everything starting at P one position down, and will insert the 99 at this point. 2 things happen. First, insert returns a new iterator, which will point to the newly inserted element, which is important. But what happened to Q? Q suddenly points to something it didn't point before. So please be aware when inserting into vectors, your iterators that refer to things into the container might be invalidated. They might not point to things anymore you are actually expecting them to refer to. Because that iterator is not being updated just because I inserted an element here. That's why Q will still, in this case, refer to a valid element, but it will not refer to 4 anymore, it will refer to 3 now. So be very careful with modification operations on a vector when you have iterators pointing into the vector. Please never do that, because you will have quite some surprises if you do. What if we erase that 99 from it? We call erase by passing in P, which refers to the element we want to erase. And erase gives me a new iterator back again, which points to the element that comes after the erased element. And that is important because I want to have a valid iterator, no matter whether that was the last element or not. On the other hand, Q is invalidated in the same way. So whenever you use erase or insert, please always use the return value appropriately to reassign it to your iterator you're working with. Then P at least stays stable. So when vector elements move, they move when you insert and erase, so the iterators might get invalidated. Be aware of that. Now let's look at a list. A list looks very similar. It has a pointer to the first node of our list. It exposes the iterators, it exposes begin and end, and it exposes erase and insert. Same functionality. So what will happen if we have a list? We do the same thing with a list. Begin iterator, increment it 3 times, assign it to another iterator, increment again. So we will have this situation. We have a list of 6 elements with 6 nodes. P will point to 3 and Q will refer to 4. Now we insert a 99 into that list at P, which will give us this, right? It will insert a new node in between and just rearrange the pointers in between the nodes. That's what a list does. By the way, that's why a list is a preferred data structure whenever you have to insert and delete in the middle very often. Because the delete and insert iteration on a list is, what complexity does it have? Anybody? Is it ON as well, as for the vector? It's probably O1, right? Because it doesn't matter where I insert it, it's always the same amount of work. That's why it's O1. That's a good thing of a list. It's very quick to insert things and to remove things because it involves only 2 point operations in the end. Again, insert returns the reference to the newly inserted element. So Q is not affected. For a list, iterators are not invalidated. Well, except for the element you're actually deleting. But all other iterators stay the same. Even if I remove that again, as we will see, Q doesn't change. So let's remove it. We will get the old data structure back. P now points to 3 and Q still points to the element 4 as before. So list insertion and erasure doesn't invalidate iterators. That's something you have to keep in mind. So while the containers have similar interfaces, they might have slightly different semantics in what they actually do. You have to, as always, you have to know what you're doing. There's no way around that. Okay, and the last one is a static array in C++, which is called std_array. Just for the sake of it, looks very much the same, but since it's a static array, you can't erase and you can't delete. You can't insert or erase, obviously, because a static array, you can't change the size. Okay, now to the point, as I promised in the beginning, why is it so important for us in the context of this course to understand what standard algorithms actually do and how they work? Well, the reason is parallel algorithms. Because C++ implements, it gives you versions of all algorithms: sort, unique, reduce, for each, transform, copy. All algorithms exist in a parallel version, a version that is parallelized for you. So if you decide that you want to, you have some code, you have written it using the sequential algorithm, and the amount of data is so large that it might be useful to actually do parallel application of that algorithm to your data, then all you have to do, you have to pass an additional first argument to the algorithm, which will give you access to a parallel version, a fully parallelized version of that algorithm. There are, by the way, 4 predefined execution policies. These things are called execution policies in the standard. Sequential, if I pass sequential here, then, well, it will do the same as the sequential algorithm. When I pass par, I allow parallel execution on different threads. And unsec and par unsec are policies that enable vectorization. So use vectorization of the facilities of the hardware that are called vectorization. And we will talk about vectorization in one of the lectures. So let's not dwell on that at this point. So the main benefit of these algorithms in the context of our course is that we have parallel versions of all of them. And that means that converting the code you wrote using the sequential algorithm into something parallel is a no-brainer. If you were writing it as a loop, as you suggest, well, good luck. You have to rewrite the whole thing. And that's why I'm so insistent that you start thinking about using those algorithms in your code wherever you can. And that certainly means that you have to know all the 100 algorithms that are available. It's always a good idea just to look at the documentation. And that's not all of them, by the way. So there are many, many algorithms available for essentially any task you might want to do on a set of elements, be it sorting, be it copying, be it, I don't know, finding things, and so on and so on. So there's a whole flurry of those algorithms, and all of them exist in parallel versions. So turning your code you wrote in your homework assignment into something parallel and possibly speeding it up by a factor of n is only one argument away, nothing else. And that is the importance of these things. That's why I'm talking about these things so extensively, just to make you aware of what the benefits are. Okay, any questions? I'm just on time. Great. Thank you for coming. See you next week. And we will talk about iterators and ranges next time.